Hi all. The next reaction in this class is going to be the radical addition of HBr to an alkene. The reaction that will actually go through a radical mechanism is the second one. The first one you should remember from a previous course. It's a Markovnikov addition of HBr. And we're going to see how by adding peroxides or light or heat we can switch the mechanism from an alkene addition mechanism to a radical mechanism. So I mentioned that we could switch the mechanism by using light or peroxides or heat, switch it to a radical mechanism. Whereas this first reaction is an alkene addition. In both cases, the carbons of the double bond gets something, and I like to indicate that with two arrows to remind me that each carbon will either get a hydrogen or the halide, in this case bromine. Why don't you try to recall the mechanism for this reaction, and you can compare it to mine. I'll also write it out. The first reaction is the Markovnikov addition of HBr to an alkene, and it is a reaction that you should have learned in a previous course. Here's the overall reaction. We do form a racemic mixture. We run this reaction with HBr. Maybe sometimes people specify that it's in the dark or it's at cold temperatures just to avoid the radical mechanism pathway. Markovnikov is a type of regioselectivity. It tells you where exactly to put the atoms you're adding. Regioselectivity is a selectivity where you pick one constitutional isomer over the other, or a set of constitutional isomers over another. Because you notice here, in this case, we added the hydrogen to this carbon, and we added the bromine to this carbon, and we don't get the other product, the reverse. So that's why we consider this regioselectivity. We enrich in this constitutional isomer. The mechanism is pretty easy. You just use the double bond to grab the proton and you kick out bromide. Again, this arrow here starts from the middle, so it doesn't really indicate which carbon gets the hydrogen. You have to use Markovnikov's rule to determine that the hydrogen should go on this carbon, thus producing a tertiary carbocation. If the hydrogen had went to the central carbon, then we would have gotten a secondary, a less stable carbocation. Anyway, we created a bromide, and you know that opposites attract, so this is the nucleophile. It attacks the carbocation to form that bond, and because this is a carbocation, it is sp2 hybridized. Right, that carbon's sp2 hybridized, and you know that is shaped as trigonal planar. It is flat. So when this bromine comes, attacks the carbon, it can either come from the front as a wedge or from the back as a dash. So you will get a racemic mixture, which is a 50-50 mixture of enantiomers. If you need to draw out the two enantiomers, probably the easiest way to do that is just to make one bond dash and one bond wedge, and do the opposite for the enantiomer. And we have this. We have that. Okay. Let me draw out the mechanism for the non-Markovnikov addition. Okay, so now that hydrogen goes here, and the bromine goes on the less substituted carbon. And this happens simply by just adding heat, light, or peroxide to this reaction up here making it go through a radical pathway. I actually put the main intermediates on the right, and we saw that for the Markovnikov addition you go through the more stable carbocation, and for the non-Markovnikov addition we're going through the more stable radical, and that will pick up the hydrogen. For the radical mechanism where we add HBr in a non-Markovnikov fashion, I actually have a typo. I misspoke. We definitely need peroxides and either heat or light with those peroxides. Let's get rid of this ore. Okay. And that will help us, that will put us into the radical mechanism pathway. So here's the new reaction, radical addition of HBr to an alkene, and we are going the opposite of what we saw previously, and so the regioselectivity is called non-Markovnikov addition. And here I chose light to put with my peroxides. We do get a racemic mixture. We'll talk about that at the end because it's actually a mixture of now 4 products because we have 2 chiral carbons. In the initiation, we take our peroxide and we cleave it to give us our CH3O radical, and then instead of that operating on our alkene, it reacts with HBr to create the Br minus radical. The Br radical. So this is what goes into our propagation step, our first propagation step. Alright, so how did we get the radical now on the more substituted carbon? You take the pi bond and one of the electrons meets up with this electron from the bromine to make a bond between this carbon and the bromine, and purposefully we'll put the radical on the tertiary carbon. So this is tertiary. Now the thing is, you know that alkenes are planar, trigonal planar. So there's our first opportunity to get the mixture. We now have this chiral carbon. I'm not going to mark it up. We take this radical, and you know that radicals themselves are planar. So when this H is added, that hydrogen can come from the front or the back, giving us another set of enantiomers. Okay, so you want to be able to compare and contrast this mechanism with radical halogenation to an alkane. Remember, in that reaction we had hydrogen abstraction to create the radical. Here we're using a pi bond, and now this carbon has only 3 bonds, so this becomes the radical. Alright, as you know, propagation, the reaction or the step keeps going over and over again because we create this Br radical that can be shuttled back here and start the process all over again. Look at the termination steps. I chose, technically you could have termination with the CH3O radical, but it's really in such small amounts that it's very rare that you'll have termination with this radical. It's more likely that you'll have a termination with the Br radical, which is equimolar concentrations with the alkene. Anyway, here we have those 3 combinations of Br radical and the radical from the alkene. Now, here, sure, we could shine light, so this is okay, the first termination product. All you have to do is shine light, and you can get back a bromine radical. But the other 2 terminations are not good, right? This one we can't reverse, and we're not going to ever get back the product. And this one also is no good. So unlike Br2 addition or radical halogenation with an alkane, where you can get the product also from the termination step, Here, we can't get the product via the termination step. So it is imperative that we keep the radical concentration low to avoid termination. Keep radical concentration low. How do you do that? By not initiating by not converting all of the HBr into Br minus. I keep saying Br minus. Br radical. Okay, that's it for this reaction. Let me draw you the stereoisomers that are created. Again, it's regioselective, right? So we are not getting a mixture of constitutional isomers, but this is not stereoselective because of the trigonoplanar intermediates. Those are terms that you should be familiar with. Regioselective, correct? Because it's non-Markovnikov, but it's not stereoselective. Okay, let me draw you those four products. Our product, without any wedges and dashes, is shown here. We have two chiral carbons, and both of them will be 50-50 RNS. These are the four products. I would still consider this a racemic mixture because we have 50-50 of these two enantiomers and 50-50 of these two enantiomers. But in the whole reaction mix, then that would mean that each of these compounds is 25% of the product mixture.